Hi guys, welcome to the fourth episode of Building Tensorflow, and you know, so I've been away for a while mainly because of bugs in the build TensorFlow, like really inane, frustrating bugs that I've been facing. I haven't resolved all of them, but we'll see what they are exactly. And today we're going to cover a lot because this is an episode that I'm recording after a while. So when I was actually testing this thing for you guys. I was able to code up a template based tensor class which can actually take in vectors now, because everything in machine learning is you multiply matrices and vectors. So it makes sense for us to move on from atomic data types like float and int to vectors, and templating is the best way to do that, since we can find out if our network works well in floating point 32 data points, or FP64, or even int 8. So for that flexibility we'll use templates. Apart from that vectorized tensor class, we actually uh, build up enough functionality to test the sigmoid activation function, and backpropagate through that, and check and test that the values that are coming out are good, are valid. So that's what we're going to do today. So let's get started. So the first thing we've got to do here is what are we doing here? One second. Okay. All right. So I've been messing around uh, with this code a little bit. So the changes aren't there are no changes. So we run this command. We'll also figure out how to make file work. Okay, so this works. And then main. It's 1124. Yeah, we were here last time. Okay, so anyway, so what we'll do, we'll convert this. Let's see. Okay, that's strange because it's tensor here. It's float tensor. Okay. Alright. No, just delete this. It's confusing. Yeah. So this was our code before, a float tensor. So the first thing we'll do is convert it into a template. So to do that, we just add this template keyword here, and we add a type name. So essentially what we can do here, is declare variables of type float tensor, something as float, and t1. So now we can also have tensors of ints, maybe, something like this. So this doesn't make sense. So something like this, right? So let's just rename our float tensor to just general tensor class, as we've templated it. And then what we'll do is we'll take in vectors for now, uh, just normal vectors for our val and grad. um, um, this will all remain the same. We have our tensor. Let's remove all the floats from here. So what we're doing is that right now the functionality we're coding in is multiplying tensors and everything there is to do with tensors. So then we can actually get on and code up a multi-layer perceptron, because essentially that operates within vectors. It doesn't require matrices and stuff. I've been looking into building a tensor that supports any dimension matrices, but that's slightly tricky. So I'll keep working on that, and we'll get back and update this to support multi-dimension data types, multi-dimension matrices. But for right now, we just have a one-dimensional vector. Okay, so this changes, right? Everything is a vector now. We won't have scalar values at all. So then we can actually move on to coding it, running it on the GPU, which I'm sure you guys must be very excited by, because that's exciting stuff. I also haven't run, like, I've just run basic stuff on the GPU. I'm actually looking forward to multiplying on the GPU and seeing the performance benefits that it gets. Alright, so what do we do now? Just remove this. Okay, there's going to be a lot of errors, but since I've already done this before, we'll get through them quickly, and you guys don't have to see the pain that I've been through trying to get this to work. Alright, so we have a tensor class. Where do we have this? Alright, so we had this ugly thing here, right? We can actually copy this into another CPP file, and then with our make function, we actually, if it's called operations.cpp, we can add it here and it works. But the thing with templates is that if you have a templated function definition outside of your main class, and you have two different CPP files, one having the declaration and the other having the definition, then it doesn't work for templates. So that was really annoying for me. So we're gonna use another approach. What we're gonna do is we're gonna create a implementation header file, sort of. So let's just copy this out from here and then create maybe like an operations impl.h. Actually, I've been looking into PyTorch C++ code, and they actually follow something similar to this. I bet it's much better, but we've got to start from somewhere. Okay, so alright, let's just figure this out first. Also, what we have here is this really annoying, something like this. So we don't want that. We just want something like this. So we update our operator overloading to and always we signify our tensors like this. So we update that definition here, and the error will go away, I promise you guys. Okay. Alright, this, and we've got to add, because we've got to give the address to this, right? That's another point of contention here, that if I have too many operations in a single expression, then it just goes haywire. Like there's a segmentation fault, because apparently there are some in a very complex expression, the C++ creates like temporary variables that it destroys after like it's consumed by the other operation. So these temporary operations, if I give them the address here and they get destroyed during the backprop, you're essentially backpropping through a tensor that doesn't exist. So it just goes to hell. So I'll have to figure that out, but for now we'll have to build small expressions and not very big ones. Okay, so operator tensor key. I know this might be hard to follow, but I hope it's making sense. Okay, so we have this. Alright, let's just step through this. So we give our val here, we do this, and backprop remains the same. New multiply operation gets it a tensor, and we return, let's rename this forward, because compute doesn't make sense, we're talking about backpropping and forward propping. Let's rename it forward. Uh, and I think this is fine. So we'll have to add, because it's templated, we'll have to add this expression everywhere. Then we'll have to update the add and multiply operations accordingly. So let's try to get this multiply operation to work. Okay, let's go here. Alright, and this will be a template, type name t, right? Right. And then this will be a tensor template type. Everything is going to be updated. Everything is going to be updated. So we do this, rename this, everything tensor, right? Now we'll actually keep this as vector of t, because you don't actually need a tensor for gradient. Gradient is ephemeral, it can go away, because we're already storing the gradient in our flow tensors anyway. We don't need to have a tensor pass through. It's gonna, I don't know, let's keep it simple. And this will be forward, right? And then multiply operation, and then we just change this, and we'll just change, I don't know what happened, vector brand template type name t. You're gonna add everything everywhere, and this thing everywhere. Tensor, and this should be done. Alright, this looks good. Let's go to multiply operation. This also looks fine. No. Alright. I think this looks good, right? What do you think? Let's do the same thing with add operation. This gets real tedious real fast, because we're going to have to make the divide operation, and then the exponent operation for the sigmoid, right? I swear I'll make this code better. Like, right, I'm not happy with this code at all right now. Okay, so we have operations implementation. Let's code this thing out. Template. Just everything everywhere. Okay, I'm gonna add a template t here. I'm God for Visual Studio Code, right? Am I right? God, these errors. Get away from me. So let's add a header files. sorry, I just copied it over from my what I've already done. So this should be, let's rename our tensor.h to, a simple tensor.h. And where we were here. Let's see, we've got a multiply operation, we've got an add operation. Backward. Okay, yeah, so our function definition is a vector now. Why? Yep, all good. What's up? Vector is not a template. So what's wrong? Vector is not a template. Backward. Okay, so add operation, we forgot to do this essentially to degrad, and this is forward and exponent main form. Yep, this looks good. Okay, now what's the problem? Vector is not defined. It is defined. It's defined in multiply operation. No, it's defined here, right? Oh, we gotta add our vectors in our base class of operation. Let's add it here. So this error should go away. It has. Amazing. So what we have here is grad into this.t2.val. This is but the problem here is that this won't work because previously we had a float value as grad, and this was also a float value, and that's triple data type for C++ to multiply. So we'll have to overload our vectorized our vector class to support multiplication and addition. Alright, so let's do it. What do you say, guys? Yep. So what we'll do is we'll create a separate header file called overloads, let's say, and then what we'll do is include vector first of all. I'm betting vector has header guards. Does it? It does. Lots and lots of header guards, so we don't need to worry about including vectors all over the place. C++ is not that great a language to code in. It's so complicated, and there are like dozens of errors here that I've not experienced right now, but I did earlier. But I know better now, I guess. But the Python isn't that confusing. I still am not that sure about pointers and how to allot and delete memory in a safe way, and the weird behavior if I even when I need to store the gradients, and I backpropagate, and if I overload my expression, half of the tensors are gone, they're killed by the compiler because of temporaries. So all that stuff you don't have to worry about in Python. So anyway, we want to overload our vectors to support addition and multiplication, right? So let's do this. Namespace std, and then let's create. So the way you overload an expression, an operator for a vector is very simple, as it's the exact same thing that we did in our class actually. operator star vector. So we have a left value, which is, which will sustain in the memory, and then we have a temporary, which will be a right hand value, which will get destroyed as soon as we move on to another expression. That's what we don't want. uh, that's the problem here. So anyway, so I'm just gonna try to basic multiplication code. So for int I, okay, sorry, for int I equal to 0, I less than no, let's say a dot size I plus plus. Let's add assert 2 here. Let's say assert a dot size equal to b dot size, and tensors are not the same size. This is a trick to actually print out the error message with the assertion, and I'll have to include assert.h, I think. Library with C++ knows. Alright, a dot size, so let's say d equal to ai, so vi, then r pushback. I really have a lot of respect for C++ programmers, because what they do is a hard job. They deserve to get paid a lot. Python programmers have it easy, I think. Yeah, but I think you're more productive in Python though, much more productive. Tensors are not of the same size. This is correct, right? So let's just create one for addition. Let's just add it here. Okay. This should do it. So let's test this out, shall we? Okay, 1 and 2. So what we need to do is create a tensor. Tensor 1 vector flow 2. This will be a float. So that's what the API looks like. Okay. If I go backward, we'll have to build a print function, for easy debugging, and say, alright. Okay, the computer is hanging. This should be fine, and let's have like a print function here. Print vec. plus feature here. And then same thing here for templates. See what you do. Into everything. Okay. Yep. To backward, we need. Okay. So to backward, we need another vector of this. Yep. We have it. Plus does not match anything, doesn't it? Okay, let's check this out because this works into. Okay, alright, we've commented this out, so let's uncomment it out, see that what we're doing is fine, and 2 4. Yep, I think this is fine. Alright, missing a semicolon here. Do you think it'll run? Really want to run in the first try. Of course not. It doesn't. Has no member. Okay. Let's debug this thing right now. Backup does not exist. It does exist. What are you talking about? Okay. Public operation, expected class name before. Okay, yeah, I get it now. Yeah, so we did not do this. So that's the first error. And now class Tensorflow has no member called backprop. That is just not true. What's this then? How the hell did you not find this? Okay, let's move up. These errors. Has no member front top, has no member back off. Oh, okay, what's happening here is something really simple. We aren't including this header file. My bad guys. So main.cpp, we just, after including tensor, I think we include our implementations. Operations idea.h. Yep. So now, okay. Maybe we include here. How about that? Okay. Tensor.h. Okay, let me see. We include our operations afterwards. Alright. Okay. So what's wrong here? The class Tensorflow has no member called backprop. Okay. So these are the only errors, I think. Missing template arguments before something. Okay. Missing template arguments. Okay, we're missing some template arguments. Tensor T. Small errors, Sorry. Um, okay. Is there any other class tensor? Just front of. Okay. So now let's try to debug this thing. Problem is in line 38, this front up forward. Okay, nice. Why though? Front up is null here, back up is here. There's no operator front up. If we do, it's public, right? Okay, let me just try to debug this. Okay, maybe let's set this. Okay, the error changed, right? No match for operator star this d1 Okay, so we need to uh, include the overloads.h in our implementation. Include overloads.h. Okay, there's one more error. No matching function for call to std vector float multiply operation t. Okay, tensor t is std vector float. This this is line number 16. Okay, so this is a problem. Why not? So this is our vector of t, and this is our operation. It overloads, right? Operation. Oh, okay. And I think anywhere there's an error. I think I'm missing a template. Yep, it's done. So let's try to run this. 1124. That's exactly what we wanted. 1124. Just we vectorized it. Amazing. 2, 3, let's say 4, 5, let's say 10, 12. So we should have 2. Sorry. Okay, that's a problem, tensors are not of the same size, but they are, aren't they? Oh, yes, thank you. Assertion error. Okay, we need one command to compile it and run it, so that's where the makefile comes in. Main.cpp. Let's create a build folder, right? And then we'll git ignore it. Build main.o, and then build main.o, and then do we want it late main.o? Not really, not for now. So if you just make this error comes, I need to rename this. I think that's the fault of the editor. Yep, it's done. So it's in our build folder right now, as you can see. So we just delete this. Delete. So yeah, we figured out how to build it also. So the makefile is really useful there. and we figured out that auto works. I just used it right now. I didn't know that if it will work or not. So that's a relief. Anyway, so we've done our addition and multiplication. uh, let's continue on. Let's do this dia thing. Let's do the sigmoid also. So for sigmoid, what we need is an exponent operation and uh, division operation. So let's do that. Dot h, exponent operation dot h, and then we have a division operation dot h. Okay. Rename division operation dot h, and then what we do is we just copy this over to a division and our exponent. So then we'd have what we'd have it exp. Let's do that. Exp exponent operation, right? Nothing fancy. So exponent operation just has one, so we don't really need another one. So we just have one here, and that's all there is to it. And then division operation should have division. This all remains the same. We just add a different header card here. Everything, we have to specify everything in C++, otherwise it just goes haywire. So you've got to be really aware and be ready to go in deep to debug, and debugging is a nightmare. So we have to be really careful with how we code. So yeah, this is it. So right, so this is a good format, right? We just define it here, then we implement our stuff here. So we implement it here. We probably have to divide this into chunks, or else it's going to get unmanageable really fast. So let's first do our division operation. Include a header file, division operation here and here, and then we'll have I think this video is gonna be long, really long. So for division, the back propagation for division is something like this. So you guys can do it by hand. So I'm just gonna mention what the backprop for division is, and you can see if that's right or not. So for if x divided by y is forward, for grad for df by dx equal to grad that comes in by y, because because 1 by y is the constant here, and x just when you differentiate it, it goes away. For df by dy, it gets slightly trickier. It goes grad into x into the y comes up, so it comes up, you have a power of -1 on y, so -1 comes down when you differentiate it, and -1 is then -1 is added to the -1, so it's equals -2, and that's divided by y squared. So that's our entire that's a division back propagation. So for exponent it just remains the same, so that's really trivial. We just have to multiply the the forward pass value into by the gradient and send it backwards. So to code this, so what we'll have to do here is grad divided by this dot t2 dot val. So we'll have to overload this, and then we'll have to overload a lot of stuff. Okay, we'll have to overload this symbol. So let's just write this down so that we have a clear idea of what we want to do. So t1 is fine, and then star -1 -1 is fine, and then star star -1, and then star -1, and then divide t2, I think, right? This t2 dash val, and we need to overload 2. So that sounds good, right? Yep. So to do this, what we'll do is let's head on to our overloads. Okay, let's overload this stuff. So this is quite simple, just divide this, and then we also need we also need something like this. For a scalar multiply, scalar divide. I think we might need to do that with the multiply too, but we'll do that later when we have the need. But because the sigmoid operation needs this, a scalar divide. So because we need a 1 by x operation, so that's why we'll just scalar overload. That's a vector divide, and then we need to do it both ways, right? So this is really annoying. We actually don't need the scalar divide, right? We actually don't need the scalar divide on the other side. We only need it here. So this is it, right? That's all we want. And then I think we need a scalar multiply too. Okay, let's just copy this out. Scalar multiply. I should write more comments, but I think I'm too lazy. Star, and then we'll have like b dot size. That's fine. All right, and then let's have a power operation also. Scalar power operation. Let's override this. and then let's say you have like a vector, and then maybe const b a dot size power a I, right? This is to the power of, we need this, so we need to compute the square of something, and we'll need that in the ME mean squared error loss, maybe. Yeah, definitely. So might as well define this here. A power operation, and this is what does this do? This so this looks good, right? So we need to, for the power operation, we need C math. We need C maths. I think that's fine. And for scalars, we remove the assert. So remove the assert for now. We'll clean up this code afterwards. Scalar. Okay. Alright. So run this. We have a power operation, and we need an exponent operation too. So let's go back to implementations. This does look fine, I think, but the thing is, we need to typecast it to a float or whatever data type we have that's coming in. So what we do here is, just divide this expression. This is getting a bit complex. Let's say vector d temp equal to this. Okay, and let's have temp into, let's have this typecast minus 1 divided by this dash d2 dash val, and then exponentiate it, and then let's typecast the 2 also. So this is essentially our equation. It looks really complex, but it's just this. Okay, we're good. I think we're good. -1. As you can see, I'm a basketball fan. I subscribe to all those NBA talk shows, which have really opinionated guests. It's a really good thing to watch when you're mentally spent. Funny to just see both of the debaters go at it. Some of them are really funny. Like Shannon is quite funny. Temp 1, temp into. Okay, this looks good, doesn't it? I'm just not sure. Let's just add this bracket here and this thing, and then let's check our overloads again. So if we're doing actually the right thing here, so divide operation is t of a here. We actually don't need this. Let's not have this. A scalar multiply. Let's just keep the divide, and we have a dA here and a const of dA to b. That should be good. Yeah, that should be good. Let's add an exponent too. Vector create a function called exponent, and then we'll have vector ta. For an exponent we don't need another thingy. For power operation, we do need this, I think. Right, for an exponent operation what we just need is an exponent. That's enough. Power operation, scalar divide, addition, multiplication. Right, I'll also include the source code of all this in the link of the videos. I haven't done that as yet, so you guys can look and peruse it to your do whatever you guys want to do. Whatever seems best for you guys. So this is done. Also we need to make changes in tensor.h to so let's just say let's divide it, new divide operation, and then let's create exponent exp. And no, we don't need an exponent. We need what do we need? We need a new exponent operation. Yeah, we don't need anything here because new exponent operation, and then just give this to it. And that's it for now. Let's see if this works. I think it will. So we have our overloads overwritten and everything overwritten. So what we just do here is let's just see if this runs. Okay, does not name a type. Okay, so I think we're not including the exponent operation here. Let's do that in Tensor. Okay, we haven't included anything actually. Divide operation dot h. Let's include exponent operation dot h. Division operation, or rename. Let's call it divide operation. Divide operation is overloads using namespace xdd. Okay, overloads implementations has multiply operation, divide, multiply operation. New divide operation does not name a type. Okay, expected a primary inspection for this. Alright, so I think we're not including, we're making some sort of mistake. Divide operation. Divide operation is fine, I think. Are you sure that's the error? VIDE operation. Alright. Tensor. Divide operation. Okay, so I think. Oh, alright. Divide operation. operation, and let's just change it here. Simple. Nothing to see here. Oh, we forgot to add the backprop and foreprop for the exponent also. We do that just now. Just let this error go away. Tensor, right? Divide operation. Yep. This is good. Yep. No errors. Amazing. So let's just add our backprop and frontprop for the exponent, and then we'll be done. We'll have, and then we'll just check the sigmoid case. What's the forward prop and what's the backward prop? Exponent operation. Okay. Exponent simple. Exponent is d1 not well. Simple. This is very simple. I love the exponent. And we backprop through grad into exponent. This dot g1. Nothing to see here. Alright, I think this is right. Let me just check once. Exponent, this one is the forward prop and the grad. Yep, this is good. Alright, so let's do a sanity check here. So I've already coded the sigmoid function test. Let me just copy paste it here and print. Let's rename this print tensor because that's what my code runs with. Sigmoid test. I hope this runs. Yep, it runs. And for reference, let me just check this real quick. So I'm using CS 231N 231N's backprop example. So W0 X0 W1 X1 W2. That's exactly what we're getting here right now. So the first value is minus 0.196. That's approximately minus 0.2, so that's fine. The other one is 0.40. This one is 0.3933. I think that's fine. They CS231 has flowed it or sealing it, constrained it to 2 decimal points. So this is minus 0.4. That's fine. This minus 0.6. That's 589. Yeah, approximately. That's fine. And the last one is 0.2.196612, and we have successfully done the sigmoid test and it works. Yay, amazing. But you must have observed with our current formulation we have to declare our tensors and then have this whole big chunk of one-step computation. So what I was telling you guys about having I was telling you guys about having one big expression, but that doesn't work because that is the main problem here. So let's try to have one big expression of the sigmoid that resembles the sigmoid, right? Let's have something like, so what was the expression? This is W0 into X0 plus W1 into X1 plus W3, and then we into -1 into -1 um, into -1, and then F into D into E, then all of this dot exp, then we add 1, and then let's say 1 divided by this. So this, so obviously this doesn't work. A lot of errors here. I don't know where to get started, because the problem here is if you multiply and you multiply here, you can't add them up, because these the tensor formed here is a temporary, the tensor formed here is not a temporary. The right hand side is always the temporary, so this disappears. Even if I get it to work by, you know, removing the ampersand sign here, just maybe maybe doing this, right, and then this might go away, but it just doesn't anyway. So like, even if I get it to show no error, the temporaries die. So, but we can't have our tensors die in the middle, so hence lies the problem of, you know, we have to declare each computation and, you know, store that tensor in a memory and not let it get destroyed, because we have to backprop through everything. So that's the disadvantage of having operator overloading. Even though it's awesome, you've got to have a lot of equations. That makes for bad code. I'll try to figure this out, so that, you know, there's some way to not let the variables get destroyed. One approach is, you know, declare them on the heap and then let it go, so because then it will always be in memory. But then yeah, we can do that. That's a good option. I'll have to look into this, and when I do, I'll be the first to let you guys know, of course. So this has been a long lesson, and we achieved quite a lot though, and we have our like really nice you know, building and compiling and running makefile, and then we have our very small main file. You know, it's except for the sigmoid test, it doesn't do much. It just overloads it. It just calls a tensor class and just calls operators implementations, and that's it. We can abstract this too in another header file, but that's fine. And then the tensor just has nothing much. It has all the operations, and then it just defines what each operation does. Not a lot here. It just backpropagates, you know, the core functionality. And then we have our multiply operation, divide operation just defined here, and the main chunk of the processing happens, you know, here in the operation implementation. The backprop and the front prop happen here, and even these are overloaded, so we don't have to, you know, do complex multiplication and division, because the overloads have everything, the tensors overloaded. And so now what we can do in the next lesson that I'm really excited about, and I don't know anything about that myself, is run the multiplication on the GPU and see how fast it is. That'll be a really cool experiment and get us one step closer to actually becoming on par with those Google and Facebook engineers who code these frameworks and have really great knowledge of C++ and optimizing our neural networks. that's a really nice skill I think everyone should have who's working in deep learning, because for example, I'm actually coding an object detection algorithm for self-driving cars right now. So what that entails is that mask RCNN and YOLO are really great, but they're not optimized to run on a CPU. As They've mentioned how to do it, but there's no good open source implementation for actually running this thing on a production worthy car. So I have to code a loss function called the focal loss on the GPU, because it's really slow in regular Python. And for those speed savings, knowledge of GPU programming would be a really big help. It's not very complex actually, and these frameworks give you an idea of how to do that, but you just have to know CUDA programming. That's something you just have to know. And hopefully with this project we'll get closer to knowing how to code on the GPU. Alright, see you next time. Next time we'll, I think, run our computations on the GPU, and let's leave it at that for now. I'll try to find a solution for this big sigmoid test and try to shorten it down, but don't have much hope for it in the short run, because we have to get to other things now. Alright, see you guys. It's been great. See you in the next episode. Bye bye.